Hello everyone, this is Module 4 of Chemical Processes in Biomanufacturing. So we're going to go ahead and jump right into a lecture. So some tasks that require knowledge of chemistry as a process technician: identify and label chemical materials using chemical symbols, monitoring chemical reactions, storing and disposing of chemicals safely, reading standard operating procedures, and safety data sheets. Separating materials from a mixture, identifying chemical hazards, preparing chemical solutions, collecting samples, and using instruments to analyze those samples. So, and analysis is a huge part of being a biowork technician. This part is not in the book. The reason why I introduced this is because the book goes into some details that make more sense when I kind of give you some background information. Okay? So one atom, think of, water's made of H2O. One atom would be like one hydrogen atom. So you have two hydrogen atoms and one oxygen atom in water. Think about one hydrogen atom. So each atom is made up of protons, neutrons, and electrons. Protons are positively charged and have mass. They are located in what's called the nucleus, and I'll give you a picture of that in a second. Think about this positive as a nucleus. Neutrons have no charge, they have mass, and are also located in the nucleus. The point of neutrons, even though they don't have a charge, is to bring stability to the nucleus. Otherwise, because opposites attract, protons and electrons would just smash together. And you want electrons on the outer part of the nucleus in clouds around the nucleus. Not in the nucleus. Electrons are negatively charged. They do not have very much mass, so we don't add that into the mass number. What is the mass number? We'll talk about that in just a moment. Okay. This is a simplified model of the atom. If you have taken chemistry or you go on to take chemistry, you'll find out that it's more complicated than this. But for right now, I'm not going to make you cry. Okay. This is the model of the atom we will work with for this class. So you see this particular atom has 3 protons, 3 neutrons, because remember the neutrons are green, and 3 electrons. When we look at the periodic table, the number of protons will tell us what the atom is, and the number of protons is the same as the atomic number. What do I mean by that? Okay, so let's look at, if we have 3 protons, we're looking at lithium right here. The smaller number is your atomic number, the larger number is your mass number. The smaller number is your atomic number, the larger number is your mass number. We have 3 protons, so this is lithium. The atomic number is always the same as the number of protons, always, always, always. If your number of protons changes, the element automatically changes every single time. You cannot have 2 elements with the same number of protons. Period, end of story. The mass number is always the bigger number, and it's made of neutrons and protons because remember, those two have mass. Electrons, again, do not have enough mass to be added to this mass number. So this mass number is made of protons and neutrons. Okay. If you want to calculate the number of neutrons, we will round this up to 7, and we would say the bigger number, which is going to be 7, minus the smaller number, which is going to be 3, so it's your mass number minus your atomic number, is going to equal your number of neutrons. So your 7 minus 3 is going to be 4. So lithium would have 4 neutrons, 3 protons, because the atomic number is 3. All right, and we will practice this. So, with this particular atom, you see that there's 2 protons. And the type of atom it is, or the element that it is indicated by the number of protons. So if it has 2 protons, let's look back at our periodic table. 2 protons, we've got to go over to 2. So that's going to be helium. So this is helium. Okay? 2 protons is helium. Oops. Protons makes it helium, like we just said. Now, because we have protons and electrons, what we can also do is we can calculate the charge. What would be the charge of this atom if you have 2 protons, 2 positive charges, and 2 negative charges? That would make it 0. It's like you have $2 in your bank account, and then you spend $2, so how many dollars do you have left in your bank account? None, right? If we had 3 positives and 2 negatives, if we had 3 positives, again, that makes that a different atom. We're at lithium again. But let's say it only had 2 electrons. We have $3 in our bank account, then we spend 2, right? Then we have how many dollars left? Positive 1. Okay, charges can also be negative. If I had 5 electrons and 3 protons, protons is like the money you already have in your account, so if I had 3 protons, but then the electrons, because they're negative, they take money out of our account, so positive 3 minus 5 would be negative 2. At that point, you would be 2 in the hole, right? Our bank account is red. We don't like to be there. It's happened to most of us, though, including myself. But that means you are at negative 2. So charges can be positive, neutral at 0, and also negative. So, the parts of the element that are going to tell us some information, you have your chemical symbol, you have the chemical name. We already talked about atomic number. We already talked about what the mass number means. And I already explained a little bit how to find the number of neutrons. When you're not given that simplified view of the atom like I gave you, when you don't have that pretty picture, this is what you're actually going to see more often. And so to find the neutrons here, you're going to do the mass number, right? Because the mass number is made of protons and neutrons. We're going to subtract the atomic number, which is the number of protons. So protons plus neutrons minus protons gives you just neutrons, right? Kind of makes intuitive sense when you know what the atomic number and the mass number stand for. All right. So here I want you to take the time to practice a little bit. So you're going to go through, you're going to find the number of, you're going to use the protons. Again, the protons tell you what element you're going to use. You're going to find the name of the element, and then you're going to calculate your neutrons like I already stated. Okay. Then you're going to use the charge to find the number of electrons. All right. And after that, we will go over this chart. Well, I have asked you to go through and try this on your own, and now I am going to walk through this with you, okay? So if our number of protons is 6, okay, let's go to our periodic table. Then we have to find the atomic number of 6. Now we have carbon, right? 6 means carbon. So I'm going to type in carbon. All right, remember to find our neutrons. We do our mass number minus our atomic number. Right? What was our mass number for carbon? Well, that was 12. We're going to round to 12 for that one. Our atomic number was 6, so our neutrons are 6. It doesn't always work out this pretty, just so you know. But it does this particular time. So, electrons. If our charge is 0, okay, if we had $6 in our bank account, because protons are like the dollars in our bank account, and then we had 0 at the end, how much did we spend? We spent $6. Okay. All right, so if we're going over to atomic number 8, that is oxygen. So we will type in oxygen. Remember, we are doing our mass number, which is always the bigger number, minus the atomic number. Wow, I cannot type today. All right, so now we are doing oxygen is 16, minus our atomic number is 8. 16 minus 8 is going to be 8. All right. Now, for our, let me make that the same color as it was before. My OCD demands it. All right, so if we have $8 in our bank account, because we have 8 protons, right? And we come out with $0. How much did you spend at the store? You spent $8. And that's your number of electrons, because our charge is 0. Coming up, we're going to have an example where a charge is not 0. Okay, and we will walk through that. Again, 8 protons is going to be the same element, oxygen. All right. Our neutrons are going to be the same for this particular example. Oh, not 6, 8. Because our mass number and our atomic number are still the same. So the only thing that's going to change now is our number of electrons. All right, if we have $8 in our bank account and then we had -2 after we spent money, that meant we spent too much money, right? So how do you go from +8 to -2? You spent $10. Okay, You spent $10 in that case. All right. And now we are going to go to 12. 12 is magnesium. Oops. Magnesium. All right. And let's just go ahead and fill it in for the next one. Magnesium. All right. Magnesium, let's look up our mass number. Our mass number for magnesium is 24.31. We're going to round that down to 24. So now we're going to do 24 minus 12 equals what? 12. That's it. All right. Our charge is 0 right now. So we have $12 in our bank account. We have $0 after we went shopping. How much did you spend shopping? $12. 12 minus 12 is 0. Oops, I don't know what I just did there. Let's get out of that. All right. Again, our neutrons are going to be the same in this case. If you've taken chemistry, you know the number of neutrons can change, but we are not going over that in here. So don't worry about it for this particular class. Now, if we went to the store with $12 in our bank account and at the end of the day we still have $2, okay, how much money did we spend? We spent $10. All right, and this is an example of how your electrons change. You see how magnesium and oxygen, when they have charges, have the same number of electrons, but they have different charges and they're different elements. Okay, so this is how we are going to calculate protons and neutrons and electrons. We're at a place where we are starting off with what's in the book. When you're a process technician, if no one explains the answers to these questions, ask a supervisor before proceeding. What chemicals will I be working with or around? And may I have all the safety and health information about these chemicals? Safety data sheets should be readily available to you. Companies are required to train you. And these are the things on the screen that they are required to train you on. You need to know where the SDAS files are. You need to have task-specific training on how to handle the chemicals that you're handling. There needs to be methods to detect hazardous chemicals in the work area. You need to know about any physical and health hazards. Physical hazards would be like if there's something you can cut yourself on, if you could fall on. You need to have personal protective equipment, which is what PPE stands for, and standard operating procedure information, SOP information, for handling workplace chemicals safely. And you need to have information about the company's chemical labeling system. Every time I work somewhere new, even if it's in academia, I need to know how that particular place or lab or pharmaceutical company labels their chemicals. Exposure limits. So you're going to have exposure limits. Those are listed in the SDS. So the way that they're listed, 3 milligrams per cubic meter, means that there's 3 milligrams per cubic meter of volume for the room. And that would be an exposure limit. If you're consuming this in any way, even if it means breathing it in, 10 milligrams per kilogram fatal, which this isn't for everything, this is just an example. This means for every 10 milligrams per kilogram of body weight, this should not be here, is fatal. Let me take that out. Is fatal. All right, so you'd have to know, how much you weigh in kilograms in order to figure this out. Slideshow from current slide. All right, sorry about that. Safety data sheets. So safety data sheets have 16 sections. They're the most important resource for your chemical safety. It is your right by law to see SDS sheets. Technically, there can be electronic copies, but if your electronic system goes down and you still have to come to work and do your work and you don't have paper copies, that's illegal. Okay. Whenever I'm running a lab, or I'm in charge of a lab, that's why I prefer paper copies and I prefer to update it. And also having an electronic copy, like sometimes depending on where you work, particularly in academia, sometimes security needs a copy of those things in case someone gets exposed to something. It's good to have both paper and electronic copies. You can't just rely on electronic copies. If your electronic system goes down and you do not have access to it, that is against OSHA regulations. Chemical fires. Many chemicals are flammable. In the event of a fire, if it happens in our lab and you're one of my students, just get out because you're not trained on how to put out a fire. Okay? Get out. I should be calling for help, but if for some reason I'm incapacitated, knocked out, whatever, you can call for help. Do not try to put a fire out with a fire extinguisher without proper training. So just leave and call 911 if needed. All right. Chemical spills. You want to know what's in nearby lines and tanks as a process technician. You want to verify process conditions before starting a pump or opening or closing valves. You want to check hose and pipe connections before starting or stopping flow. It's easier to prevent a mess than it is to clean it up, pretty much. Keep containers of chemicals closed when not in immediate use, and practice good housekeeping. Elements and atoms. We have already gone over this, okay, most of this. Atoms are electrically neutral, but sometimes can lose or gain electrons, making them positively or negatively charged. We've talked about that a little bit. We haven't talked about the fact that if it is charged, it's called an ion. Again, if you take chemistry, you have taken chemistry, you know if it's positive, then it's a cation. If it's negative, it's an anion. But we're not going to get too deep into that here. Just know that you have ions, and they are quite reactive. Because it has that positive or negative charge, it's seeking out something to become zero again. Chemical reactions happen because they have gained, lost, or shared electrons. We already talked about electrons, what electrons are within one atom, but they can be pulled off by another atom or shared. So you can have different types of chemical reactions. We're not going too deep into that, but just know that chemical reactions happen because electrons move. Families of compounds, this is just for your background information. If you're working like in a lab as opposed to like a process technician, you may get deeper into this. I've only worked in 2 different process technician jobs. I didn't have to know a lot of this, but it's good to have background information in case you move into more of a regular laboratory setting. Acids and bases. So you have alkalinity and pH. So alkalinity is another way of saying something's basic. So it can be acidic or alkaline, or acidic or basic. So alkalinity is just another word for basic. Measuring and controlling pH is an almost universal task amongst biopharmaceutical technicians. You're going to need to know how to measure pH and how to keep it within a certain range. Here's our pH scale. Neutral, water is about 7. It's slightly acidic, natural water. Acidic is less than 7. Basic or alkaline is above 7. In order to do these problems, you literally just type it into the calculator. Okay, you should have a log button on your calculator, on your scientific calculator, so you're just going to literally type negative log of whatever it is. Make sure you type it in correctly. That's the biggest mistake I see, and you'll get the answer. Okay, it doesn't always come out this pretty as a whole number. It only comes out very pretty as a whole number when it is a multiple of 10. Like this doesn't look like a multiple of 10, but if you moved the decimal over a couple times, you could. And so because you can move the decimal over 1, 2, 3 times to get 1, this comes out to be 3. So technically you could do this problem without a calculator, but let's say it was 1.1, which is not a multiple of 10, then you would have to use a calculator. The way they used to calculate this back in the day without a calculator, I looked up and it literally made me cry. It's witchcraft. Don't worry about it. Just use your calculator. Same thing for this problem. You can move it over 1, 2, 3, 4 to become 1, and so the answer is 4. But again, just use your calculator if that doesn't make sense to you. All right, and here's some videos for you to watch. All right, 2 factors to determine how hazardous a particular solution of acid or base is strength and concentration. Strength and concentration, both together. So what is strength and concentration? Strength is the reactivity of a particular acid or base. You can have something that's really strong and reacts fairly quickly. Concentration is you're talking about how much acid or base is present in a particular solution. Again, if you've taken chemistry, you've done stuff like converting grams to moles and having molarity as a point of concentration. If you've ever had a pool, you've probably heard of parts per million. We also talked about different ways of measuring concentration before: osmolarity, osmolality, um, spectrophotometry. Those are all different ways of figuring out how much of something is in a certain volume of liquid. In this particular case, though, we are talking about acids and bases. Strong acids are more hazardous than weak ones. So weak acids would be like acetic acid, which is also called vinegar. But industrial strength acetic acid is 99% glacial acetic acid. Now, the vinegar that you have in your house is very much diluted. And so that concentration of vinegar is safe for your house. But industrial acetic acid is not safe. Just like the acetone in fingernail polish is safe, but industrial acetone that's used to strip paint off of houses, not nearly as safe. An example of a strong acid would be like hydrochloric acid. When you think about that, it's like, oh, okay, that's something that might give you a burn if you touch it, if the concentration is too high. Mixing in water and acid. The curriculum says do what you order, add acid to water, but I find that it's easy to mix it up even though it kind of rhymes. I just remember water first. You want to put water, acid, and then maybe a little bit more water before you add more acid, because if you do it the other way around, it's going to heat up and it can explode. So there's been times where I've worked in the lab or I was making chemicals for a lab, and even though I did this, I also had to do it on top of an ice bath. Okay, that's how reactive some acids are. So just remember, what comes first? Water comes first. Water first. Water first. Water first. Always, always, always. There's very few always in chemistry. This is one of them. Water first, always. Faster reaction rates with increasing concentration. So when you're talking about how fast something reacts, if something's more diluted, you have less particles within the same volume. So let's say these two things are 1 liter. This both has a liter. The more diluted it is, meaning the more water you add to it, the less you have. Let's say we are diluting hydrochloric acid, which I've done before. Diluted hydrochloric acid, these each represent a HCl molecule. You're going to have less. So they're not going to bump into each other as much due to that exchanging of electrons. This is kind of like when you have the classroom that doesn't have so many students, so you can spread out, but then you have those classes that are full, and so that's more concentrated, right? You have more concentration of students. The same thing is happening here with hydrochloric acid. It's more likely of a chance you're going to bump into each other. So think about the classroom example. It's much more comfortable, right, to be able to spread out because you're not going to bump into each other because it's uncomfortable, right? Think about if you're uncomfortable, you might react. If you're bumping into a bunch of people during a class, you're going to get aggravated. You're going to get heated, right? And that's the same exact idea here. You're going to have a faster reaction when you have more HCl in the same amount of space where you are. And in this particular case, you have to be comparing the same amount of volume. Okay. The same thing happens with pressure, right? Imagine if I took this and I push down on it, and if I push down on it, I'm pushing everything closer together, right? Imagine if the volume in the classroom suddenly divided in half and everybody had to sit on the same side because half the tables were taken away. That's more uncomfortable, right? There's more of a chance you're going to bump into somebody. So with increasing concentration and increasing pressure, you have faster reactions. Probably think of table salt, which you use at your kitchen table. Table salt's made of sodium chloride. Salts are the products between acids and bases. So an acid and a base comes together to make salt and water. This is because acids donate a hydrogen. Bases donate an OH. So then you're going to have 2 hydrogens and 1 oxygen as one of your products. They're going to come together to make H2O, which is water. The other 2 things that came with the acid and the base, depending on what they are, they come together to make a salt. All right. Organic compounds contain carbon and hydrogen. For this course, you can just remember carbon, but technically CO2, carbon dioxide, is not considered an organic compound because it doesn't contain both carbon and hydrogen. So, carbon is an element that can form a number of bonds with many other elements. This is why there are so many organic compounds, because carbon can make 4 bonds. Okay, and if you go forward to take chemistry, you'll know why. We're not going to worry about that here because I don't want to make you cry, but carbon can make 4 bonds. That's why it's so versatile. That's why carbon is considered like the element of life. Because of carbon-based life forms, I'm sure you've heard that in documentaries somewhere, carbon is very versatile because it can make 4 bonds. Energy changes. So you have endothermic reactions, which means it requires heat from the environment to keep going. When you cook, the act of cooking is an endothermic reaction because you are putting heat into the reaction in order to get your food to cook. That is an endothermic reaction. An exothermic reaction pushes energy out, so that is a energy release in the form of heat and can be dangerous. Some of them proceed so fast and with so much energy that they cause explosions. An exothermic reaction example is a bomb. Okay? Again, chemical reactions are chemical changes. Chemical changes meaning that you can't go back to what it used to be. Like dissolving sugar in water is not a chemical change because technically you can still separate the sugar and water. But when you burn wood, you're not taking that wood and putting it back. You're not taking the ashes, and making them back into wood, right? So these reactions change one or more elements into different chemicals that you cannot. Now, some reactions are reversible. You've learned that in chemistry if you took chemistry, but we're not worrying about that here. So, chemical reactions cause chemical changes, meaning that you've made a change and it's something completely different now. They occur again when elements meet and when you have the breaking and forming of chemical bonds, which is again those movement of electrons. This all involves movement of electrons. And that's it for Unit 4.